All right, so let's talk just a little bit more about the infinite solution case. And if you remember, we had used this example earlier to show, how you recognized that you had a system with an infinite number of solutions, right? A dependent, consistent system. So the question is, if you have solutions, then how do you write them down? So in the infinite case, here's the thing we're going to do, and this is going to be, we'll do this something similar when we're in larger systems, 3 by 3 and 4 by 4. Once we know that we have an infinite number of solutions, and for the 2 by 2 case, here's how it looks. But once you know, what you do is you just pick one of the equations, pick the simpler equation. Say this one looks simpler to me, right? And let's you can do this several ways. Probably the easiest thing to do is this: your solutions are going to have an x part and a y part. We're going to actually start with y. We're going to start with the last variable. And we're just going to say this: y gets to be anything it wants to be. Okay, this is how you handle infinite solutions. You pick one of your variables and say you get to be whatever you want to be. And to indicate that, we'll use t. We'll say y can be t, and t is called a parameter. And a parameter is something that we can use to, or that we're allowed to choose the value of. So in the infinite case, y gets to be whatever it is, we'll call it t. Whatever it wants to be, we'll call it t. And then all you got to do is figure out what x is, right? You pick y to be t, and then you just figure out what x is. What that means is you take your equation and you substitute in the value of y, which is going to be t, and you solve it for x. So in this case, come back here, 2x will equal 4 minus 6t, x equals 2 minus 3t. So what you get is you actually get what we call a parametric solution. Okay, the parametric solution is the x part that we just found, comma the y part, right? Isn't that how we write our solutions? X comma y. But what we do is we give the solution in a formula form. That is to say, this is the formula that gives you solutions, and basically the idea here is you get to pick t to be whatever you want. So for instance, if you say, oh well, let's let t equal 0, plug t equals 0, then you get the solution what? 2 comma 0. 2, 0 is a solution to our original system. But what if we pick t equal to 1? Then the solution that we get from the parametric formulas, or from the parametric equation, is what? Negative 1 comma 1. Negative 1 comma 1 is a solution. Okay, and you could keep going this. We don't need to do this, but this just demonstrates, let's say t equals 17, then we get the solution of 2 minus 50. We of course would pick a complicated one. 2 minus 51, so minus 49 comma 17. That is a solution. All right, so we don't need to actually go through and write all these down. We just give the formula with the understanding that t can be anything we want, and once we choose t, then we have one of the infinite number of solutions. So that's how we'll go through any system that has an infinite number of solutions. We'll designate the last variable to be a parameter t, and then we'll solve for the other variables in terms of that parameter. Okay, what we want to do now is let's just quickly take a look at how we deal with 3 by 3 systems. All right. Now the challenge with solving these systems with live TV is that I invariably make simple little mistakes here because you're doing a million little simple calculations. All right. When I'm in a live classroom, I have you guys to right away tell me that I did something wrong. I added or I subtracted or I multiplied by 3 or multiplied, just did the multiplication wrong or something like that. But when I'm recording, I just have to hope that I get it right, because I could go through the whole problem and solve it and not know that I made a mistake. back on step 2 of a 15-step process. So I hope I don't do that, but I will probably, you'll probably end up with a video where I've made some mistakes. But let's try to keep that to a minimum. Anyway, here's a 3x3 system, right? Linear, all the variables are linear, 3 equations and 3 variables. So our solution should be an x, a value for x, a value for y, a value for z. And like we've said all along, there are only 3 possible things that can come from this. Either you get 0, 1, or 0, 1, or an infinite number of solutions. All right, so what we're going to do is we're going to do elimination. At this point, we're just going to use elimination again. And so what you do is you can do things like swap the order of these equations if you want. But what we're going to do, and that doesn't change the solution, of course. So here's how you want to do this if you're just solving a system using straight elimination. You want to try to find 2 equations, and from those 2 equations you want to eliminate one of the variables. Okay, and so you try to pick some that might already be set up. In this case, I don't see many that are set up, so what I'm going to do is I'm going to use this equation and this equation, and I'm going to eliminate the x variable. Okay, so thinking ahead, if I want to eliminate the x variable, that means I'm fine with this being a 3x. If I can make this a minus 3x, then when I add those 2 equations, the x variable will be eliminated. All right, so here's what this looks like. I'm going to take the first equation and multiply it by a minus 3. See, there you go. Try that again. Minus 3 times x plus 2y plus z equals 4. Did you not click that button off? My videos would be half as long if I didn't make that one mistake again and again and again. But I'll do it again, I'm sure. Okay, making sure that I copied everything down. So I'm going to multiply that entire equation by negative 3, giving me a minus 3x minus 6y minus 3z equals negative 12. And I'm going to add that to the second equation. Now I could have gone 1 and 3 or 1 and 2. I can pick any 2 I want and eliminate any of the variables. I just happen to pick the first 2, and I'm eliminating the x variable. I'm free to choose. Okay, so that if I add now, the x's are gone, and I'm left with a 2y plus 4z equals 8. All right. Now what happens is I actually now before I move on, let's introduce some notation here. What I have done here is I've taken minus 3 times my first equation and added that to my second equation. Okay, so we're going to use this notation to keep ourselves straight. Minus 3 times row 1 plus row 2. And then what I'm going to do with the new equation is that's going to be, I'm always going to replace one of the 2 equations that I used with this new equation. In this case, I'm going to replace row 2. Okay, I could replace row 1, but you'll see here in a second why I would replace row 2. And now I get a new system. And when I say new, we're putting in this new equation that I got from here as my second equation. Hopefully copying everything down correctly. All right, now let's talk about this for a second. It's a new system, but it's what we call an equivalent system, in that the solutions to this system, or the solution to this system, is the same as the solution. By doing this, by multiplying a row, which is totally fine, and adding 2 rows, I don't change the solutions. So it's an equivalent system, and I'm happy with it. All right, but it's simpler, right? Because I've got rid of the x's. Okay, so now we go again. What did we do the first time? We used row 1 and row 2 to eliminate the x's. Okay, that was a free choice. But now on this second elimination, we aren't free to choose. Number 1, we have to eliminate x's again. Number 2, we have to use the row we didn't use. And so we're going to use row 1 and row 2. or sorry, row 3. Here's what we're going to do. We're going to take minus 2 times row 1 and add that to row 3. And the answer I get is going to be my new row 3. Now, here is why I back up here. I replaced row 2 instead of row 1. Because I like row 1. If I'm going to eliminate x's, I like that x is just has a coefficient of 1. It just makes my math easier. But in reality, I can do whatever I want. Here, I'm going to replace row 3. All right, so let's write this down. Minus 2 times row 1. So that's going to be minus 2x minus 4y minus 2z equals negative 8. There we go. I was doing so good. Minus 2x minus 4y minus 2z equals negative 8. Row 3 is 2x plus 7y plus 9z equals 23. And so when I add those, the x's are gone. I'm left with a 3y. I'm left with a plus 7z. And I'm left with a 15. That's going to be my new row 3. X plus 2y plus z equals 4. 2y plus 4z equals 8. And my new row 3 is this. 3y plus 7z equals 15. Now I want you to understand something here. There are many ways I can solve this original system, but using elimination, but they all follow the same pattern. Step 1, pick any 2 rows, eliminate any of the variables. Okay? We picked 1 and 2 and eliminated the x's. But I could have picked, if I was really crazy, I could have picked 2 and 3 and eliminated the z's. Step 1 is just that. Pick any 2 rows, eliminate any of the 3 variables. Step 2, though, is forced. Again, you've got to eliminate the same variable you eliminated the first time, and you have to use the unused row. All right? So the reason I say that is because if you happen to choose a different combination of rows to use, all right, you'll get a different looking system, but it's still equivalent. All right, so that makes it a little challenging if you're like trying to follow along. You might be eliminating these two and replacing row 3, whereas I used these two and replaced row 2, and so you'd get a definitely different system. Well, you just have to trust your work there. All right. So as long as you do it right, you'll end up with the same solution. All right. So what do we do now? Notice what we've done at this point. We've done elimination twice, right? And now we end up with this little 2x2 system. So what we're going to do is we're just going to focus on that 2x2 system, and we're going to do elimination and solve that 2x2 system right there. This guy's just going to hang out for a while. We're just going to solve this 2x2 system using elimination. So what are we going to do? I don't know. Let's say we eliminate the y's. All right. So to eliminate the y's, we multiply, let's go 3 times row 2 plus negative 2 times row 3, right? That should give us the 6 and the minus 6, and that will replace row 3. So that looks like this. 3 times row 2 is 6y plus 12z equals 24. 3 times row 2, let's double check, make sure we're okay. Minus 2 times row 3 is a negative 6y, that's what we wanted, so the y's are eliminated. Minus 14z equals negative 30. And so when I add those, the y's are gone, which I wanted. I get a negative 2z equals negative 6. Okay? Now, I should write that up here. That's going to be my new row 3. I can do one other thing. When I get to this point, or any point along the line, I can kind of do this. I can take this entire, I notice that entire equation is everything is a factor of 2. So if I multiply it by 1/2, right? So what I'll do before I actually write my new system is I'll do this. Let's go negative 1/2 times this row 3, and that replaces row 3. In essence, just divide everything there by negative 2 to make it simple. It only makes sense if everything's divisible by negative 2 at this point. If this was a 5 or a 19, you don't have to do it at this point. But that's an easy simplification to do. an easy way to get a simpler equation. So we're going to do that. So we've got x plus 2y plus z equals 4. That's our first row. Our second row stays the same. And our third row, thanks to this additional bonus change there, where we're dividing by -2 or multiplying by -1/2, that gives me z equals 3. Okay, this is where we want it to be. In particular, we have 3 equations. This is an equivalent system, so if I can solve this system, that will have the same solutions as the original system up there. Notice the 3 equations. The first equation has all 3 variables. The second equation has just the y and the z. In other words, the x is gone. And then the third equation is missing an x and a y. That's why we did these steps the way we did. So that we kind of get this little stair step thing. We call that echelon form. We'll play with that a little later on. But once I do that, once I get a single variable in the bottom, 2 variables in the second, 3 variables in the top, I can solve it, right? Because I start at the bottom. Oh, z equals 3. I don't even have to do anything. If I would have even used that equation, I could solve for z and still get z equals 3. So, want to keep track of that. That's the z part of my solution. And then I back substitute, right? Once I know what z is, I'm going to take that value of z and I'm going to substitute it up into the equation above. So, doing that little bit of work right here, it's going to be 2y plus 4 times the z value equals 8. I think this is going to give me 2y equals, that's 12, 8 minus 12 is minus 4. Y equals -2. Alright, so there's the y part of my solution. And then I back substitute those into this top equation and solve for x. X plus 2y plus z has got to equal 4. Z is 3. So x minus 4 plus 3 equals 4. That's a -1. I think x equals 5, right? X equals 5, and there's our x coordinate of the solution. And so what's our solution? X, Y, Z. All right, and that's our solution. And of course, remember with systems of equations, you can always check your solution by plugging them back in. Okay, by plugging them back in. And it should work. All right, now we need to add this little piece. This video is already long, but I don't want to make another video for just this little piece. In the zero solution case, right? This is the one solution case. How would you know if you got 0 solutions? Well, you would end up at some point in this elimination process with an absurd equation, a 0 equals 7. All the variables disappearing and the right-hand side not disappearing, not being equal to 0. So if that happens at any point, that's how you know you have 0 solutions. What about an infinite number of solutions? Well, here's what an infinite number of solutions would look like after you did those eliminations that we talked about. Because you don't know beforehand, right? You have to go through the elimination process. The entire elimination process to get to this point. You don't know, coming out of the box that you're going to have an infinite number of solutions. So during the elimination process, you're going to end up with this kind of a deal, right? In other words, that last elimination is going to eliminate the entire bottom equation. That's what tells you have an infinite number of solutions. So how do we handle that? Well, remember our solutions are going to be, there's going to be a z coordinate, a y coordinate, and an x coordinate. Here's how you handle it. We're going to create a parametric solution. And the way we do that is, for simplicity's sake, we're going to always make it the same. Let z equal t. And now you need to figure out what the other variables are going to be in terms of t. Well, using this equation, if z equals t, we plug that in here, y is going to equal 7 minus 4t. So y will equal 7 minus 4t. That's the formula that's going to give you y if you know what t is. and then we substitute back into there to figure out what x is going to have to be, right? So x minus 3, now notice what I'm putting in for y. I got to put in the 7 minus 4t plus 2z, 2t. And now I got to do a little math, do a little algebra, simplify. So x, we're going to get crazy here. We're going to add the 12 and the 2 to get a 14. So that's going, and move it across. It'll be a minus 14t. We move the 20, add 21 to both sides. We get a 26. So look, we get a 26 minus 14t. All right. And so our solution, written parametrically, would be there's our x coordinate, there's our y coordinate, and there's our z coordinate. And that's our parametric solution. Now here's the deal. We will always, for sake of simplicity, just start by setting z equals to t, the last variable in the pair, as your parameter. But you could set x equal to t and solve for the other variables. What that leads to is a slightly different parametric solution. The formulas will look different, but they will yield the same solutions. Okay, you could set y to t and you would get a different looking parametric solution, but they would yield the same solutions. And you can try that if you want, right? You can come back in here and say, oh, another way I could do it is this. I could say, oh, let's y equal t, and then back substituting, if y equals t, z is going, I'll just do z real quick. Z is going to equal what? 7/4 minus 1/4 t. That's way more complicated, right? I mean, that's not because we chose y. It's just because that is the way it is. And I just did that by solving that for z in terms of t. And then x will be another complicated formula that I have to find by back substitution. So this would give me a different looking formula, but it's important to understand this parametric solution formula would give me the exact same solutions, right? So the parametric solution, parametric formula is not unique. So what we do in order to do our best to make it unique is to kind of follow this convention of letting z equal t and then solving for the other variables. All right. Okay.